So this video is on section 1.3, determine the maximum or minimum of a quadratic function. And this is something that you most likely did a lot last year in grade 10, and really determining the vertex, because we know the vertex of a parabola gives us the maximum or the minimum. And two ways that we kind of went about determining the vertex in grade 10 is either you can find the zeros, we either factoring a quadratic formula, and we know that the vertex is right in the middle, or the axis of symmetry is right in between the two zeros, and that's how we get the x value. And then given the x value, you can find the y value of the vertex by plugging into the equation. But the most common technique that you probably did last year was go off and completing the square. And so we're going to start with a review of that, because once we complete the square and have our equation in vertex form, then we determine the vertex, and then from that we determine the maximum or minimum value of the function. So let's do a review of completing the square. And then we'll state if that function has a maximum or minimum value and what that value is. So the easiest way, it's not the only way to complete the square, but the easiest way to do this is to factor out your a value in your equation. But we don't want to factor out the a value from everything. We just want to factor out the a value from our x squared term and from an x term. So here we get 4. So we factor out from the 4x squared, we get x squared, and then plus 2x. Now I'm going to leave a lot of space before I put the right parentheses, because one of the things that we need to complete the square is add, subtract something to those terms, and then we just have the minus 5 at the end. So the sort of algorithm or formula to know what we add and subtract is we take our new b value and we divide it by 2, and then we square it. So this is going to be 1 squared, which is 1. So I write this out explicitly because seeing this 1 is going to help us later on. Now, the purpose of us adding 1 was to be able to make this trinomial into what we call a perfect square trinomial. So there, you might have practiced this a lot last year. Recognize a pattern within perfect square trinomials is that when we factor it, we get x plus or minus our root, and then quantity square. So that's how we get looking at vertex form. But in order to make things fair, we just can't just add 1, we have to subtract 1. So this is a common trick in mathematics, and sometimes when we sort of add 0 to an equation, because we can't change the truth of that equation, or can't change the value of that equation. So adding 0 does not change the value of that equation, but we could represent 0 in many ways to achieve certain different things. So in this case, we're going to add 1 and subtract 1. And again, the whole purpose is there so that we get the first 3 terms. It's going to be a perfect square trinomial, so that it factors, and I'm going to switch to square brackets now, so it factors the x plus 1 quantity squared. Okay, so this is why I like to write this part down, is because this number, if you would like to remember a process, fits into there, into the x plus 1 part, quantity squared, and then we're still left with a minus 1 minus 5. Okay. Now the next step is we want to distribute the 4 to get rid of the square brackets that I created. So we get 4 times x plus 1 quantity squared. We don't want to expand that, or else we just undid what we did. And then 4 times the negative 1 is the negative 4, and then minus 5. And finally we simplify that to be 4 plus 1 quantity squared minus 9. So therefore this has a vertex of negative 1 and negative 9. Again, my trick to sort of remembering what the x value, the coordinate of the vertex, is taking what we are squaring, in this case x plus 1, and we want to make that 0. Again, the fundamental concept of quadratic is 0 squared is 0, and that's the only way we get a 0. Anything else gives us a positive answer, which explains why we have a minimum in a quadratic. So in this particular example, because the a value is positive, it's a positive 4, so therefore opens upwards. So in this case, this has a minimum, then min value of minus 9. Again, our minimum or maximum value is always the y coordinate of our vertex. So let's walk through this next example. It's a little bit more tricky because it deals with fractions, but we take the same steps. So here we're going to say g of x is equal to, so we're going to factor out the negative 2/3. So I get x squared. So here, when I factor out a value, I'm dividing by to get to what's left. So 6 divided by negative 2/3 is the same as 6 times negative 3 over 2, which is negative 18 over 2, which is negative 9. So x minus 9, x squared minus 9x. And again, we're going to add and subtract something to make this a perfect square trinomial. Well, unfortunately, 9 does not divide nicely by 2. So this is where we're going to get to some trickiness, or not some trickiness, but some dealing with fractions in order to get our vertex form. So here, again, our algorithm to get that value added and subtracted by is we're going to take a b value, divide by 2, and square it. So that's going to be 81 over 4. So we need to add 81 over 4 and subtract 81 over 4. So in this equation, we don't have a constant, or we don't have the c value, so there's nothing after those brackets. And here, again, this trinomial here, we know the reason why we add 81 over 4 is we know that this is going to factor to x minus 9 over 2, which is why I sort of wrote that down as a visual for help me remember what that value is going to be, and then minus 81 over 4. Then distribute the negative 2/3. So I get x minus 9 over 2 quantity squared, and then I'm just going to write this all full, so just do the fraction arithmetic. So 81 over 4 times negative 2/3. So this is going to be minus 2/3, x minus 9 over 2, and then negative 81 times negative 2 over 3. Well, this simplifies, or reduces to 2, and then 81 divided by 3 is 27. So this becomes negative 27 over 2. So therefore the vertex is negative 2/3 minus 27 over 2. Because our a value here is negative, this parabola is going to open downwards. So therefore there's going to be a maximum. And its maximum value in this case is minus 27 over 2. So that's a bit of a review of completing the square, and that's actually a considerable amount of work if we want to figure out the vertex. So the purpose of today's lesson is to see a technique, which we'll call partial factoring, in order to determine the vertex of an equation that is in standard form without having to go off and complete the square. So there's our success criteria. So determine the vertex of a quadratic function by, well, this one is actually review, completing the square, which we just did above. The new method we're going to learn today is going to what we call partial factoring. And hopefully you will see that the process of doing that is a lot faster. These next two ones are really kind of review. Determine if a quadratic function has a maximum or minimum and state what it is. So we did that above already as an example. And finally, the last thing is we want to find the equation of axis of symmetry given any quadratic equation in standard form. So again, the equation of axes is where the parabola is symmetrical, and the symmetrical right at the vertex. So the axis of symmetry is that vertical line, and it has the value x equals the same x coordinate of the vertex. So really, x is equal to xv. Whatever the x coordinate of the vertex will be, that's our axis of symmetry. So consider the function f of x squared plus 4x, and we want to graph the function below. So there's a couple of ways that we go off and do this. One is we could sort of just factor this. So this is another way to find the vertex. We could complete the square on this, but I'll just show you the other way as a refresher on how we could go off and determine the vertex of this. So we need to find the zeros of it, and then we need to factor it. So we can factor a 2x, and we're left with x plus 2. So that implies that 2x is equal to 0, or x plus 2 is equal to 0. So one of the zeros is 0, and the other 0 is minus 2. So I'm just going to graph that. Let's put it under scale. So there is 0, and there's negative 2. Now, in order to get the vertex, is we need to take the average of those two x-intercepts and divide by 2. Well, taking averages because we have 2, we have to divide by 2. So the x-coordinate of the vertex is the sum of my two roots. Oops, it's not positive 2. So negative 2 over 2. So that's going to be negative 2 over 2, which is negative 1. So in order to calculate the y value of the vertex, is we need to plug in the x-coordinate of the vertex. So this is why we have function notation. Makes it easy that way. Of 2x squared plus 4x. So in this case, it's f of minus 1 is equal to 2 times minus 1 squared plus 4 times minus 1. And here we get 2 times 1 minus 4, which is negative 2. So therefore, the vertex is at negative 1, negative 2. And there we could draw a parabola. So we just really need 3 points. We need our vertex and then the points on either side of the parabola, and it might look something, it would look something like that. Well, let's look at the graphs on the same grid. So here we have g of x is 2x squared plus 4x plus 2, and we also have h of x, which is 2x squared plus 4x minus 6. So really, what's the difference between g of x and f of x? Let's explore that one first. Well, essentially, we have the same part, 2x squared plus 4x, and we're going to add 2. So really what we're doing is taking every single of our answers from f of x, and we're just adding 2. So here we can see that the vertex happens at negative 1, negative 2. So we're going to move that point up 2. So let me graph this function in green. So taking the vertex, adding 2 up, and we do this likewise with their roots. So one of the roots is 0, 0, so that becomes 0, 2 now. And the other one will happen at negative 2, 0. So that's going to be negative 2, 2 now. Okay, so basically our entire graph, and this is the idea of why we have a vertical translation when we add or subtracting something to a previous function, because we're taking an answer just adding or subtracting a certain value. So in this case, g of x would look something like this. Okay. Our other example, which I'll do in maybe blue, is in this case it's the same function, but we're subtracting 6. So the same idea as we have a purple graph or f of x, and we're taking each of those values, every single of those y values, and we're subtracting 6. That's really the difference between f of x and h of x. So really our graph shifts down by 6 units. So let me do this point or vertex of negative 1, negative 2 becomes negative 1, negative 8. And likewise, our roots shift down by 2. Sorry, not by 2, by 6. And our parabola looks something like that. Okay? So now that we have those 3 graphs, we just want to see what similars we see in all 3 of them. Well, going through, if we did this in class, some people might say, well, they're all the same shape. I'll put that in quotes. And maybe I would be more specific and say, technically we're saying it's the same stretch factor. So they all have the same shape. Others may say, yes, they're all pointing upwards or opening upwards. Maybe that's a better way to say it, opening upwards. So there's a lot of similarities that we see, but the main one that we want to look at is the axis of symmetry. It's the same on all of them. In other words, the vertex and all three functions fall on the same value of the x-coordinate. So here is our, let me try that again. So there would be the equation of axes of x equals minus 1. And the vertex falls through all of them. So that's the axis of symmetry. But more importantly, we said that the axis of symmetry is really the same x value of the vertex. So really, in essence, all three graphs have the same x value of the vertex. Well, this is a powerful thing that we could take advantage of. So let me write this down. The other thing is that they all have the same axis of symmetry. And this is important because this implies that they all have the same x-coordinate of the vertex. So what we can do is that now we've discovered this common characteristic. Now for any value of k, what we can do is find the x value of the vertex ignoring the k value. In other words, we could just look at 2x squared plus 4x, find out what the x vertex is. So in this case, we discovered that the x coordinate of the vertex is minus 1, and then therefore the maximum or minimum is going to be f of minus 1. Okay? So let's use partial factoring to determine the vertex of each of these. So the first thing we want to do is, given our function g of x, we want to create or define another function, and we can't call it the same because g of x is g of x. That's what it's defined as to be. It's minus 12x squared minus 48x plus 5. So here we create another function p of x, to me short for partial factoring, and all we're going to just do is take our x squared term and our x term and define it to be that. Now we know that g of x and p of x is going to have the same axis of symmetry as we've shown above, and therefore they have the same x value of the vertex. So in this case, let's look for the zeros. So we want that to be 0, and I'm going to factor out the minus 12x at the same time. So I'm going to get 4x plus 4. Sorry, not 4x plus 4, 4x plus 1. No, sorry. Really not on the ball. X minus x plus 4. Sorry, x plus 4. So therefore, this implies that minus 12x is equal to 0, or x plus 4 is equal to 0. So we got our two zeros. So in this case, x is equal to 0, or x is equal to minus 4. So in order to get the x coordinate of the vertex, we need to add our two roots and divide by 2. So this is going to be negative 4 divided by 2, which is negative 2. So to get the y coordinate of the vertex, let me do this over here. So f of xv is going to be negative 12 times negative 2 squared minus 48 times negative 2 plus 5. So in this case, this is minus 12 times 4 plus 96 plus 5. So negative 12 times 4 is a minus 48 plus 96 plus 5. And negative 48 plus 96 is going to be a positive 48 plus 5 is going to be 53. So therefore the vertex is negative 2, 53. In this case, because it's opening downwards, as a max of 53. Okay, so that's an example of using completing the square to partial factoring to get our vertex. Doesn't actually ask for the maximum, but that's fine. So let's look at our second example. Again, I'm going to define our function p of x is going to be 9x squared minus 7x. So the nice thing about partial factoring is that we don't actually have to factor out the a value. Okay, like we did for completing the square, we had to factor out the a value in order to easily find what value to make a perfect square trinomial with. And that's easy to do when a is 1. So in this case, we don't actually have to factor the 9. We just factor out x. So now we're left with 9x minus 7. And again, we want to find the zeros of that. So this implies that, well, x is equal to 0 for 1, or 9x minus 7 is equal to 0. So that implies that 9x is equal to 7. Divide both sides by 9 gives us x is equal to 7 ninths. So in order to get the coordinate of the vertex, we're going to have to add our two roots, divide by 2. So in this case, that's 7 over 18. So it's going to be a little bit tricky because we're dealing with fractions, but not too bad. In order to get the y coordinate of the vertex, we need to do f of the xv. So that's going to be 9x squared. So 9 times 7 over 18 squared minus 7. Oops, I gotta go back to the original function, plus 1. So minus 7 times x, which is in this case 7 over 18, minus 1. So let's do our fraction work. I need to pull a calculator here. So 7 over 18 squared. So 18 squared is 324. So 9 times 49 over 324 minus 49 over 18 minus, so here I must find a common denominator of 324. So 324 over 324. I don't think 324 is divisible by 9. Oh, it is. It's actually, this comes out to be 36. So let's change this to be 36 over 36. So let's continue this down here. So this reduces to 49 over 36. So here you get 49 over 36 minus, well, need to multiply 49 by 2 minus 98 over 36 minus 36 over 36. Oops, our original function was plus 1. So that should be plus, plus, plus. So 49 minus 98 plus 36 is negative 13 over 36, which is 36 divided by 13 is 3. Oh, I thought it was 8. Nope, we can't simplify that anymore. So therefore the vertex is at 7 over 18, comma negative 13 over 36. Okay, so that one proved to be a lot more difficult because we're dealing with fractions, but things would have been a lot worse if we had to complete the square on that one. All right, so that's that example over there. So how can we do this in general? What can we say this one in general? So in general, for all quadratics in standard form, ax squared plus bx plus c, they share the same axis of symmetry, but have different points, and that's including the vertex. And that's because they differ by the c value. In order to find the axis of symmetry, we only consider part of the function, which is just our x squared term and our x term. So we could actually shortcut this and look at this in general, because hopefully you recognize, as the examples that I went through, one of the roots was actually always 0, because the idea of partial factoring is when we have ax squared plus bx, we could factor out at least one thing, and that's x. So we could factor out just an x, we know the roots has to be, one of the roots has to be 0. So here, how can we sort of summarize this or have a shortcut to this? is so if I have p of x is equal to ax squared plus bx, what I'm going to do is I need to find the zeros. So if I factor on x, I'm left with ax plus b. Now, that implies that x equals 0 or ax plus b is equal to 0. So in order to isolate for x, we need to subtract b. So ax is equal to minus b, and then we need to divide by a. So x is equal to minus b over a. So those are my two roots. But in order to get xv, I need to take the average of my two roots. Well, this is going to be now 0 plus minus b over a, and then we need to divide by 2. So this turns out to be minus b over 2a. So really, to the gist of it is that we want to quickly find the vertex of an equation. We just know that the x value of the vertex is always going to be minus b over 2a. And then once we get that value, we can plug that in to get the y-coordinate of the vertex. Okay, so you don't actually have to partial factor all the time. You could actually just jump to the chase and say x coordinate of the vertex is minus b over 2a. But word to the edge, if you're being asked on the test or on an assessment to find the vertex through partial factoring, you must partial factor for me. In other words, you must do this step for me over here. As I did up here, you need to do these steps to partial factor for me so that you show me the entire process. Okay, but later on, once we get down here,